Good morning, class. Welcome to the online classes for physics, class 12th. This is the last topic for your chapter magnetic charges and the magnetism, or we can say the magnetic effect of current also. So, this is the last topic, that is galvanometer. In your book, it is given as a moving coil galvanometer also, so you can see the both are same. But here we are going to see what the galvanometer is and what is the construction, what is the working principle of the galvanometer, and what is the sensitivity of the galvanometer. After this, in the next session, we will be going to start the new chapter, that is magnetism and the matter. So here we are going to see what the galvanometer is. In the practical labs, many of the students have already seen that galvanometer device, that how does it work and what does it do. It is a device which have a scaling on it, which is in the lower values to the 0, and then again increases to the value. It have to the left hand, then it have a pointer which moves to the left hand as well as to the right hands. So here we can say that it is a device which is used for the measuring in the electric. So what is galvanometer? Galvanometer is an instrument which is used for the detection of the current. So here we can say that the galvanometer's device is used for measuring the smallest current, so the small value current. So it is not used for the heavy currents or for measuring the heavy currents, because it is a sensitive instrument. Being a sensitive instrument, it cannot be used for the heavy current. So galvanometer is a device which is used for measuring a small currents, and mainly just to give out the practical works, we are used to measure the value of the current, and for that the galvanometer is used. So galvanometer is a device which is used to detect the current in the circuit, but of the smallest value. Okay, so galvanometer have a pointer on it which shows the value of the current by rotating that pointer. So moving pointer tells us about the electric current moving in that wire or that instrument. So what is galvanometer? If it defines, then a basic device for measuring a small electric current by the help of the electromagnetic force produced by the current. So before that, we have seen in the last class that whenever a rectangular coil or a circular loop is allowed to kept in the magnetic field, then it experiences a torque, that it experiences a pair of or a two pair of forces that are working on its two ends. So we can say that the torque is a force, that is pair of forces that is acting on the ends of the coil. So what does it do? If we are taking a current loop or circular loop or a rectangular loop kept between the two magnets, because magnets will allow them to provide the magnetic field. So whenever a loop is kept in the magnetic field, then this rectangular loop or the sheet of the current carrying conductor, then this allows to move. And why this moves? Because we know that the magnetic field anywhere due to this magnet will show by the magnetic field lines. And what does magnetic field lines do? We know that they are the current carrying instrument are always used to affected by the current and the magnetic field both, because a moving charges possess electric as well as the magnetic field both. So we know that this magnetic field lines moves from north to south in the outside, and from inner side it will moving from south to north. So what this magnetic field lines do? They are moving from south to north. Now by seeing the direction of the magnetic field, you will find the magnetic current direction also by using the right hand rule. So by taking the direction of the magnetic field as a thumb's value, we can find out the current direction also. So by seeing the current direction, we can think that what is the direction of the current and what is the direction of the magnetic field. Now we know that this magnetic field and the current always acts in the direction opposite, or we can say that they are always in the perpendicular direction. That is, the angle between them should always be 90 degree. So the motion of the charges, force and the magnetic field. So these three are always in the perpendicular direction. So we can say that whenever an object is kept in the object or the current carrying conductor is kept in the magnetic field, then this object experiences a force that is inverse and also as the outwards. So both the forces acts on that object that is normal to the paper. So these both the forces will be equal itself, equal, but of couple of forces are acting on it. So these pair or the couple of forces acting on that in the equal but in the opposite direction, inward and the outward, on that current carrying loop is said to be the torque. So this rectangular loop, let it be have the turns n. If it is having the turns n, we have seen this in the last class also, that is the number of the turns is given by n, and the current flowing in that loop be I, magnetic field be B, and A be the area. So the angle between them be theta, then the torque acting on that will be equals to NIBA sin theta. So we can write it as torque will be equals to NIA cross theta, right? Because we know that this is what some like a cross product, because sin theta is, so it will be equals to cross product. Torque is equals to NIA cross B. So these are the values for the torque. And what this NIA, that is the number of the turns of the copper wire or any of the conducting wires on the loop by the area A, and let the current flowing on that loop be I. Then what we can say, that this product can be given as the magnetic moment small m. So we can write it as m cross B. So what is the value of torque? That is m cross B. So this was the value of the tau, which I have already seen in the last session. This will be used for the galvanometer also. So that's why we have just recalled the topic. Now what is the working principle of the galvanometer? We have seen that the galvanometer is a device which measures the smallest current passing through the circuit. So here the moving coil galvanometer, we have seen that the commonly used moving coil named so because it is having a pointer which rotates or moves. You can see this in the lab also, that we have a pointer which used to move. That's why it is known as the moving coil galvanometer. Now what is the working principle on it? We know that whenever a current carrying rectangular loop is allowed to kept in between the two magnets with a copper wire wounded on the circuit. So we can say that these magnets are allowed to make two couple of forces, that is one force acting inward direction and the other force is acting outward direction. Now what these two equal forces in the opposite direction will try to, this rectangular loop will be trying to rotate. So these forces are allowed to rotate the circular loop or the rectangular loop conductor. So this rotation will allow the body to rotate. That is, the pointer is rotating is due to this itself. So we can say that this is acting in the principle of the permanent magnetic moving coil or the electric or the magnetic induction also, because electric and the magnetic field together allows this loop to move. And the second thing, galvanometer works on the principle of conversion of electric energy into the mechanical energy, because if electric energy is allowed to move through the circuit, because we are already taking a loop which is a conductor and the current is flowing through it and is kept in between the magnetic poles. So we can say that the current is there, so this electrical energy is produced and this allows the magnets are allowing this conductor to move. So this is rotating, so the energy is converted into the mechanical energy. So it works on the principle of the conversion of the electrical energy into the mechanical energy. And whenever the current flows in the magnetic field, it experiences a torque, that is the couple of forces acts on it, and it makes the loop or that object to move with an angle alpha or angle theta. But here we will be using the angle alpha also for the galvanometer. So it just allows the body to rotate, and it rotates through an angle that is proportional to the current flowing through it. That is, if it has a large value, then it is moving with a or rotate with a large angle. If it is moving with a less value of current, then it will move with a small angle. So this working principles of the galvanometer, that it depends on the current, it will depend on the circular loop, it will depend on the magnet which allows to move or rotate. That is, two forces will be acting on it, a couple of forces will be given by the torque. So torque is also acting on it and it will depend on the current also. So we will see the construction of how this galvanometer is made. So before going to this, the essential parts of the galvanometer, see, after that we will be seeing the working of it. There are the 5 essential parts of the galvanometer, that is, I already told that the two magnets will be taken, so they will be taken in the form of the U-shape, that the U-shaped concave poles. What this concave means, that they will be the bent in surface. The bent in surface will be there in the form of the U-shape. These magnets will allow the loop to move. So the flat rectangular coil of thin enamel insulated wire. So one insulated wire will also be used. a soft iron cylinder will be used, pointer will be used, so which will be rotating and will be showing the measurement of the current, and a scale will also be used which will be showing the value of the current. These are the parts of the now the construction. You can see it in the figure also that we will be using an insulated wire which is in the rectangular coil form. So we will be taking the turns which is equals to the n, and secondly it will be suspended between the cylindrical concave poles. Now this wounded wires of copper throughout this enameled insulated wire are allowed to be suspended between the concave poles of the magnet, and these strip will be used here, and it will be a thin phosphor or the bronze strip together. Okay, phosphor bronze strip will be used to suspend that rectangular loop or the insulated wire of the suitable number of the turns of the copper. Now one end of the wire of the coil is soldered to the strip, the other end will be fixed to the galvanometer and connected to the external terminal, you can say outwards, which cannot be seen. This all are the construction inside the galvanometer device, and the current will allow to flow through this, and the other end of the wire of the coil is loosed, and the spiral of the wires are connected towards the external terminal. So the soft iron cylinder and the pieces of the magnet will allow the body to move. So here we can see the diagram. We will be better understand what are the constructions. Here you can see one the top view and one will be the lateral view. Here this upper tension suspension is given here. This is the suspended wire. This is the wire which is used to suspend the particle, and these copper wires are wounded on a surface, and this is allowed to suspend between the two magnets, that is the two concave poles of the magnet, that is north and the south. And we know that whenever the north and the south poles are there of the magnet, then the magnetic field should be working on it, and this magnetic field will be showing that it is moving from the north pole to the south pole. And when these magnetic fields are moving from the north to south, then we can find out the current values. And what this current value will do, it will move in the, if you have the thumb direction, you can take it in the direction of the magnetic field, and if you take the curls, you will see the current value also, that it will be moving in direction. So we can say that this magnetic field allows the couple of forces acting on the surface. And what this couple of force will do, so if it is having two couple of forces, it will allow to move, that is F one side in one direction, and other will be the other direction, but the equal force will be acting on it, that is one on the inner side and other will be on the outward side. So these two forces are acting on the rectangular coil will allow to move. So this rotation will be done due to this couple of forces, and this couple of forces is said to be torque. So torque is allowed to move this coil in the magnetic field. So we can say that it works on the principle of the electromagnetic field. So here the springs are shouldered to the two ends. This is the down shield and this is the other shield of the string. This both are allowed to be shouldered. A light aluminium pointer is attached to this aluminium pointer is attached to the coil, which measures the deflection. Now the coil is symmetrically placed between the cylindrical poles of the concave poles of the magnet. Now cylindrical soft iron is mounted symmetrically between the poles. Now what this means, the line of forces along the circle will be allowed to rotate, and this rotation will be done due to the couple of forces, which is the torque. So torque will be allowed to move this object. So what we can say that this is the moving coil galvanometer, because the pointer is moving due to the suspension of this rectangular coil between the poles of the magnet. So the magnetic field and the current together is allowing to move this pointer. So this is a moving coil galvanometer. So what this torque will depend on. Already we have seen what is the value of torque, that it depends on the number of the turns, current flowing through the coil, area of the coil, and the magnetic field, and it will be depending on the angle between them, that is sin theta. Now since the torque is acting in the 90 degrees, so already given it as 90 degree. Here the theta is placed, let with this with a force and this with a force. So the magnetic field will be at the perpendicular direction. So the value of theta will be 90 degrees. So sin 90 degree. So it will be NIBA. So torque will be equals to NIBA. Now torque deflects the coil. This is the torque which is acting on the rectangular coil, but we know that this pointer is also moving. Now the torque deflects the coil through an angle alpha. In the galvanometer, this is moving with an angle alpha. So torque will be restoring also, because it will be moving in one direction, then again it will move back. So this is a restoring force, and this restoring torque will be given by Ka, K alpha or Ka. So this K alpha will be equals to torque. So K alpha will be equals to, what is the value of torque? That is NIBA. That depends on the number of the turns of the coil, current, magnetic field, and the area of that coil. So value of K will be NIBA upon alpha, right? Or if we take out the value of the current, then what will be the value of current? It will be K upon NIBA, that is I is, we have taken the value, so it will be NBA. So I equals to K upon NBA, and alpha is also there. So this alpha is telling about the linear scale. So I will be equals to K upon NBA, which is the constant, and this constant is a galvanometer current constant. Okay, this is a current reduction factor. So this is the constant K upon NBA. And what is the value of alpha? It is given by I exactly proportional to alpha, and if you take out this into equal sign, then there a constant will come, that is G alpha, and this G is the current galvanometer constant. So this current reduction factor of the galvanometer is given by G. And what is the value of G? That is I upon alpha, because I is equals to G upon alpha. So what is the value of G? It will be I upon alpha. So G is equals to I upon alpha. What was the value of alpha? It was K upon NBA. So we have taken the value. So G is equals to K upon NBA. This is the value for the constant, that is galvanometer constant, or the current reduction factor of the galvanometer. So the reflection produced in the galvanometer is proportional to the current through it, and the instrument can be provided with a scale or such that a scale is called the linear scale, and this factor depends on the current reduction factor. Okay, so we have already said that this galvanometer is used to measure a small current values, right? So here you can see this, which we have told already in the few topics earlier one, that the torque is acting on the conductor to move it in the inward direction as well as the outward direction. So restoring torque will also be acting on it, and what we have seen, that torque is equals to NIBA, but the sine theta is given by sine 90 degrees, so it will be 1. So it is given as area, that is NIBA, and we know since the torque is acting on the coil deflect backward also, and it's moving upward and downward, that inward and the downward direction, so it will be of restoring torque, that is directly proportional to the alpha, where alpha is an angle with which the torque is allowing to deflect. So it is directly proportional to alpha, which is equals to K alpha, and K alpha is equals to torque. And what is torque is given by the number of the turns, I, magnetic field, and the area. It's NIBA. And what is the value of alpha is given as NIBA upon K into I. If NIBA upon K, then NBA upon K will be constant, and B is the magnetic field, and I will be the current. So alpha can be given as directly proportional to current. From here we have taken G, that is a constant, galvanometer constant. So what is the value of G? It is I upon alpha, which is equals to K upon NBA. So this is the galvanometer constant, the current reduction factor. Now we have seen that the galvanometer is a device which is allowed to measure the small current. It cannot measure the heavy current because it is one of the sensitive device. So to calculate the sensitivity of the galvanometer, that how it gets sensitive. So galvanometer is said to be sensitive. It shows a large scale deflection even when the small current is flown through it. So it is very sensitive, or we can say that the sensitivity of galvanometer is increased because it is showing a large scale value with a small current also. So there will be two sensitivities, that is, one is current sensitivity and the second one is voltage sensitivity. What is current sensitivity? It is defined as a deflection produced in the galvanometer when the current flows through it. So sensitivity due to the current. And when voltage sensitivity is defined as deflection produced by the galvanometer when a potential difference is applied across its ends. So there are the two sensitivities or the sensitivities due to the two effects, that is current as well as the voltage. So the current sensitivity is given by alpha upon I, that is NBA upon K, and voltage sensitivity will be given by the alpha, that is the galvanometer constant upon the potential difference V. So it is given by NBA upon K, but V is given as IR, so there will be KR. So these are the two values for the voltage sensitivity as well as the current sensitivity. Sorry for the distribution between the class due to my mobile. So the factors affecting on which the sensitivity of the moving coil, it depends on the NBA, that is number of turns in the coil, magnetic field and the area of the coil, and K, that is the torsion constant, that is due to the restoring torque, that is moving inward direction as well as the outward direction. So it is a restoring torque, that is a constant, torsion constant. So the factors affecting which affects the sensitivity of the moving coil can be, by increasing the number of the coils we can change the sensitivity. So but the value of N cannot be increased beyond a certain limit because the volts cannot be changed, otherwise the galvanometer will become the bulky size. So increase its resistance R. So we can say the number of coils should be of the limit, so the number of the N turns should be in the limit. And the magnetic field also can be increased by increasing the horseshoe magnets can also be used. By placing a soft iron core can also be used. By increasing the area, that is a magnet, means we can say that the size will again it will increase, so the size cannot be increased, so the area should not be increased of the coil. By decreasing the value of the torsion constant, because K, here the phosphor bronze wire is used and the torsion is used in the outward and the inward, so the restoring should be of certain limits. So we can use this phosphor or the bronze wire springs to be made of the small, so that the torsion constant should also be made small. So to decrease the value of the torsion constant, there should be the small size of the phosphor bond string. Now the advantage and disadvantage of the moving coil galvanometer. What is the advantage? That moving coil galvanometer can be made highly sensitive by increasing NBA, and torsion constant can be decreased, so it can be made more effective and can be made highly sensitive. And deflection of the coil is proportional to the current passed through it, so it is easy to measure the deflection, because if it moves through the point 1, then it is deflection is 1 ampere, so we can easily calculate the current measurement. Coil is wound over a metallic frame, so eddy currents produced in the frame bring the coil to rest quickly. What is the eddy currents? That is a small current which is produced due to the magnetic and the electric field. Now what is the disadvantage? That is it's more sensitive, so it is one of the disadvantages. Second thing, current becomes greater than it can allow the galvanometer to burn. Right, the hair springs of the suspension that the phosphor bronze wires are using, so the suspension can also be burned. Okay, and why this phosphor bronze wire is used? It is because it is a perfectly elastic, non-magnetic, and it is a good conductor of electricity. So these are the reasons why we use the phosphor bronze strings. So here the galvanometer is a device which measures the small currents with the help of the linear scale and the pointer. This pointer moves due to the torque. And why this torque is due to? Because this moving coil or the rectangular coil with the wands of the copper wire is allowed to suspended between the two magnets, and these two magnets are allowed to produce a magnetic field which is putting a torque, that is a couple of forces acting on the rectangular coil which allows to move, and this torque allows the body to move with alpha angle. So here we have find the galvanometer constant or the current reduction constant, that is G, that is G is equals to I upon alpha. We have find the value of the alpha also, and we have seen that what is the sensitivity of galvanometer, because galvanometer is a sensitive element, so we can just use the values in the certain limits, that the number of the turns should be in the limits, and the magnetic field can be of any limit, but current should be in the limit, area should be in the limit, and the value of torsion constant K should be decreased so that the phosphor bronze wires cannot be get heated. So these are the values through which the galvanometer moving coil can be made more sensitive. So here the numerical see that a rectangular coil of area 5 into 10 to the power minus 4 meters square, that is A, is given, and 60 turns is pivoted about one of its vertical sides, that is 60 turns are there, so number of turns is 60, N is 60, and the coil is in a radial horizontal field of 90 G. What is the torsional constant? So here K is to be asked. What is K? So K is equals to I upon alpha, that is M upon alpha, that is NIBA upon alpha. So N is given, I is given, B is also given, area is also given. And for alpha it is given that produces an angular deflection of 18 degrees. So value of alpha is 18. So what is the value? That is 3 into 10 to the power minus 9 Newton meter per degree. So this is the value for the rectangular coil galvanometer for the value of torsional constant, that is K. So like this type of numericals will be asked. So the only formula which we have used is K is equals to NIBA upon alpha, or G is equals to K upon NBA. And for the current and the voltage sensitivity, it was I is equals to alpha upon I, and for V, that is voltage sensitivity, was given by I alpha upon V, which is equals to K upon IR. So these are the values for the torsional constant, number of turns, and different sensitivity of the galvanometer. So this was the last topic for your chapter. In the next classes, we will be starting the new chapter, that is magnetism and the matter.